A rocket engine landing on the moon in vacuum does not produce the cone of exhaust that every launch video shows. It produces a hemisphere of supersonic gas spreading horizontally across the surface. And at the thrust levels required to land a 50-meter vehicle, that hemisphere excavates a crater beneath the ship and accelerates the excavated material into a ballistic spray traveling faster than a rifle bullet in every direction during the final seconds when the engines must keep firing to prevent the ship from crashing. This is not a theoretical concern projected from models. It is documented in NASA's own plume-surface interaction research program, running for more than a decade, producing results that appear in peer-reviewed engineering literature and in almost no promotional material for the vehicles those results describe. The mechanism that produces it is counterintuitive enough that most people who have watched rocket launches, which means most people alive, have the exact wrong mental model of what a rocket exhaust plume does when there is no atmosphere to push back against it. That wrong mental model is the reason the gap between Apollo and everything designed since Apollo is not a gap in engineering capability. It is a gap in physical regime. And the regime change happens at exactly the thrust level the new vehicles require. What the wrong mental model assumes is that vacuum makes exhaust simpler. No atmosphere to cause drag, no turbulence, just a clean burn. The exhaust does leave the nozzle cleanly. The problem begins the moment it reaches the surface. On Earth, when a rocket fires near the ground, the atmospheric pressure surrounding the exhaust plume, roughly 100,000 pascals pushing inward on every surface exposed to it, confines the exhaust into a roughly conical shape, redirecting it and mixing it with the surrounding air, dissipating its energy over a relatively small footprint. Remove that atmospheric confinement, and the supersonic exhaust gas has nothing to push against as it expands. It spreads outward in every direction simultaneously from the point where it contacts the surface, forming a hemispherical shock wave that travels horizontally across the regolith at the velocities the gas carried from the nozzle. The footprint of that hemisphere is not the small circle beneath the engine nozzle. It is a circle of ground expanding outward from the landing site at the speed of the exhaust jet for as long as the engine is firing. Exactly how deep that hemisphere excavates the surface, and exactly how fast the excavated material travels once displaced, is the mechanism the promotional renders do not show, and the mechanism that the 6 Apollo landings survived only because their engine was in a different class of the same physics. The 6 Apollo lunar module landings used an engine producing 45 kilonewtons of thrust. A single Raptor engine produces roughly 2,300 kilonewtons at sea level, approximately 50 times the thrust of the Apollo descent engine. And the standard Starship configuration uses 6 Raptor engines. The instinct is to treat that difference as arithmetic. More thrust means more disturbance. Same problem at larger scale. Manage it with better engineering. That instinct would be correct if the plume-surface interaction energy scaled linearly with thrust. It does not. The force applied to the regolith scales with the square of the exhaust velocity and linearly with the mass flow weight, meaning that a vehicle with 5 times the thrust does not produce 5 times the regolith disturbance, but potentially 25 times, depending on how the exhaust conditions change with thrust level. The Apollo LM's plume-surface interaction was measurable. Surveyor lander images taken before and after engine firings in 1967 and 1968 showed clear regolith disturbance and surface erosion patterns directly beneath the nozzle, and that measurement directly informed the decision to keep the LM's descent engine as small as the mission physics allowed. The engineers who designed the LM understood that lunar plume-surface interaction was a constraint, not a detail. What they left undescribed was where the constraint became a regime boundary, the thrust level at which the same physics stops producing a survivable outcome on unprepared regolith. Lunar regolith is not soil in any sense that Earth engineering experience prepares you for. It has no moisture binding particles together. It has no root structure, no clay content, no cohesion from repeated wet-dry cycles. It has never been rounded by water or wind. The particles are sharp-edged, irregular fragments of rock, shattered by billions of years of micrometeorite impacts in vacuum, with no subsequent process to smooth them. The material has the consistency of extremely fine, dry powder in its uppermost centimeters, transitioning to compacted but still unconsolidated material at greater depth. When a supersonic gas jet contacts this material horizontally, which is what the hemispherical plume expansion delivers, it does not push the surface uniformly downward like a weight. It shears across it, lifting the top layer and accelerating individual particles horizontally in the direction the gas is traveling. Because there is no atmosphere to slow those particles once they leave the surface, they continue on ballistic trajectories at whatever velocity the plume gave them. The velocity the plume of a large lander gives them is roughly 1,000 meters per second, 3 times the speed of sound, comparable to a high-powered rifle round. And the trajectories carry those particles in every direction from the landing site, unimpeded for kilometers, before they arc back down on the lunar surface. The particles that do not travel kilometers outward travel upward along the expanding hemisphere, intersecting the vehicle that is descending into the zone of excavation. Every grain of regolith accelerated by the plume during the final 30 to 60 seconds of powered descent is a ballistic projectile whose trajectory includes the vehicle's own structure. The Raptor engines are shut down approximately 100 meters above the surface, at which point Starship HLS transitions to a set of dedicated landing thrusters located in the mid-body section of the vehicle, gaseous oxygen-methane engines positioned high enough to reduce the energy delivered to the regolith during terminal descent. Those mid-body thrusters, whose nozzles are directed downward toward the surface, are in the direct line of the upward-traveling ejecta component they themselves produce. The heat shield panels covering the vehicle's exterior during descent are exposed to the horizontal and upward components. The landing leg mechanisms, which must articulate correctly in the final seconds to absorb the landing load, have exposed hydraulic or mechanical components that the ejecta can damage in the seconds before touchdown. None of this damage happens once at landing. It happens continuously during the entire powered descent phase that occurs over the landing site, beginning the moment the plume reaches the surface with enough energy to mobilize regolith and ending when the engines cut off at touchdown. For a vehicle the mass of Starship HLS, the powered descent over the surface is not brief. The physics of bringing that mass to a controlled stop from orbital or suborbital velocity requires sustained thrust for a duration long enough that the cumulative plume-surface interaction energy excavates not a shallow scuff in the regolith, but a crater with documented model predictions of meters in depth and tens of meters in width. The crater is the specific problem that the vehicle's landing legs were not designed for. Landing legs are designed for flat, load-bearing surfaces, the flat regolith a pre-mission survey identified as the landing zone. A crater beneath the vehicle has a geometry that changes during the excavation, that varies with local regolith composition in ways no pre-landing survey can resolve at centimeter scale, and that may be asymmetric, deeper on one side than the other based on slight variations in surface material or engine thrust distribution. Landing legs contacting the rim of an asymmetric crater rather than the crater floor, or contacting the crater floor at different depths on different sides, produce an uneven load distribution on the legs at the moment of touchdown. A 50-meter vehicle has its center of mass at a significant height above the surface. The geometry of a tall, narrow structure with a high center of mass and an uneven base is one where small deviations from vertical produce large restoring force requirements. The stability margin against tipping, the maximum tilt angle at which the vehicle is still considered stable without active correction, decreases as the ratio of height to base width increases. Starship HLS is tall, and its landing legs define a base width that, while engineered for stability on flat regolith, may not provide sufficient stability margin on the variable geometry of a crater it excavated itself. A tilt of a few degrees, sustained at the moment of engine cutoff, when the only corrective thrust available is the landing legs absorbing the load asymmetrically, is not a recoverable attitude for a vehicle that has no mechanism to right itself once on the surface. In 1967, engineers analyzing the Surveyor 3 landing photographs Surveyor 3 was the robotic lander that Apollo 12's crew visited and partially retrieved in 1969. Documented that the retro rocket firing during final descent had visibly disturbed the regolith in a pattern consistent with plume-surface interaction. The disturbed zone was small because the Surveyor retro rocket was small, but the pattern was exactly what the physics predicts. Erosion beneath the nozzle, displaced regolith in an outward pattern, surface texture change extending meters from the landing point. The Apollo program used those observations. The LM descent engine was throttled to minimum thrust during the last meters of descent. The crew was instructed to cut the engine immediately after the probes hanging below the landing legs confirmed contact with the surface. The probe touch completed an electrical circuit, triggering a blue lunar contact indicator light on the instrument panel, at which point the pilot initiated descent engine shutdown, allowing the vehicle to drop the remaining distance to the surface before footpad contact. Every one of those decisions was a deliberate engineering choice to minimize plume-surface interaction duration and energy at the cost of precision and control in the final moments. They worked because the vehicle was small enough that minimizing plume-surface interaction was compatible with completing the landing. Scaling that approach to Starship HLS does not produce a larger version of the Apollo solution. Cutting the engine early on a vehicle of that mass, allowing it to freefall from a height that keeps plume-surface interaction survivable, delivers a landing impact load that the vehicle structure and any crew aboard must absorb. The kinetic energy of a several hundred-ton vehicle falling even 2 meters from engine cutoff to contact is not a controlled landing load. It is a structural event whose severity depends on exactly how level and load-bearing the surface is at the contact points, which is the surface the vehicle just spent 60 seconds excavating with its own engines. The robotic preparation mission proposal addresses the crater problem by sending a smaller vehicle to the site first, landing it and using it to compact, center, or pave the regolith into a surface that resists plume excavation. The smaller vehicle must use a rocket engine to land. That rocket engine, in vacuum, produces a hemispherical plume expansion that excavates the surface it lands on. The preparation mission has the same problem as the mission it was sent to prepare for, at a smaller scale but with the same physics. The landing pad the preparation mission creates must be designed to survive not only its own engine's plume-surface interaction during landing, but the subsequent plume from the much more powerful engines of the crewed vehicle. Because the crewed vehicle's plume, directed at a hardened surface rather than loose regolith, produces different interaction dynamics. A hardened surface resists excavation at the surface, but transmits the plume energy into the regolith beneath the pad. If the pad is not thick enough or sufficiently anchored, the plume excavates the regolith under the pad, undermining it from below, producing a surface that appears stable until the vehicle's weight transfers onto it. The NASA Human Landing System Program's Independent Review Board, which issued its assessment in 2023, identified the in-orbit propellant transfer requirement as the highest risk technical challenge in the Artemis lunar landing architecture. Plume-surface interaction appeared as a research item rather than a program-level risk, a characterization that is technically accurate because the research program exists and is producing data, and because the program has not yet reached the point where a landing attempt would test the models against reality. The distinction between a research item and a program-level risk is a function of where in the program timeline the question becomes decisive. Plume-surface interaction becomes decisive at the moment of touchdown. At that moment, it is no longer a research question. The Starship HLS development program has not landed a Starship on the Moon. It has not landed a Starship on any unprepared surface at the thrust levels and mass the Moon mission requires. The plume-surface interaction models are calibrated against subscale laboratory experiments, Apollo-era data from much smaller engines, and computational fluid dynamics simulations of regolith behavior under supersonic gas jets, all of which produce predictions rather than measurements, and all of which agree that the predictions for Starship-class vehicles on unprepared lunar regolith are significantly outside the range that Apollo's 6 landings characterized as survivable. Blue Origin's Blue Moon lander is smaller than Starship HLS and uses different engine configuration and thrust levels. The plume-surface interaction numbers for Blue Moon are better than for Starship HLS. They are not Apollo LM numbers. The physical regime that Apollo operated in, where the engine was small enough that the plume-surface interaction stayed within bounds that unprepared regolith could survive without crater formation that threatened vehicle stability, has a specific thrust threshold below which it applies and above which it does not. Blue Moon is above that threshold. Starship HLS is further above it. Every crewed lander capable of delivering meaningful cargo to the lunar surface, because it must carry the mass that makes the mission worth the cost, requires engines that place it above that threshold. The 6 Apollo landings are cited as proof that lunar landing works. They are proof that lunar landing works with an engine small enough to stay below the threshold where the vehicle excavates the surface it needs to land on. The vehicles designed to return humanity to the moon and establish a permanent surface presence are not below that threshold. They are above it by the requirements of their own mission, and the gap between what Apollo demonstrated and what the new vehicles need to demonstrate is not a gap in engineering experience, but a gap in physical regime, undocumented in promotional materials and precisely documented in the research literature that the promotional materials do not cite. The first crewed Starship HLS landing attempt will be the first time those models are tested against the real outcome. The outcome will not be predicted with certainty before the touchdown sequence begins. It will be measured by what the crater geometry is when the engines cut, by what the leg contact load distribution is at that geometry, and by whether the vehicle's attitude at engine cutoff is within the stability margin for a 50-meter structure whose base is resting on the rim and floor of a crater its own engines produced in the 60 seconds before contact. Whether those measurements agree with the models is the question the research program has been building toward. The landing is the experiment.